Hello, fellow learners! Are we all ready to learn more math? Let's go! In this video, we'll be discussing more numerical methods in curve fitting. Hello, hi mabuhay! I am your presenter for this video. The name is 𝐂𝐔𝐑𝐕𝐄-𝅅 (ROMA), currently on my second year in the course Bachelor of Science in Civil Engineering in my school, Notre Dame of Maribel University. At the end of this video, the learners will be able to understand what is interpolation and its process, learn the mathematical methods Newton's divided difference and Lagrange interpolation, and examine one's understanding of the discussion through a small assessment. Pull out your pens, your papers, and your scientific calculators. Don't get overwhelmed. This is going to be a fun ride as we try our best to learn about interpolation. Interpolation. It is one of the old mathematical procedures used to construct new data points within the range of a discrete dataset of known data points, or can be used for determining a formula of the function that will pass from the given set of points x, y. It is a method of deriving a simple function from the given discrete dataset such that the function passes through the provided data points. This helps to determine the data points in between the given data ones. This method is always needed to compute the value of a function for an intermediate value of the independent function. It has a various number of applications in engineering and science which apply in estimating varied concepts of cost, mathematics, statistics, and etc. In short, interpolation is a process of determining the unknown values that lie in between the known data points. It is mostly used to predict the unknown values for any geographical related data points such as noise level, rainfall, elevation, and so on. Now, interpolation data table usually goes like this one. Learners are often asked to solve values in between the given data, such that what would be the value of f of x if x is equal to 2.2? As shown in the second table, we have a function 1 plus 3x. Substituting 2.2 in the 1 plus 3x, we have 1 plus 3 multiplied to 2.2. Therefore, f of 2.2 of the given data is 7.6. Before proceeding to Newton's divided difference and Lagrange's method of interpolating, we'll be learning about the two base methods as foundation of the two interpolating methods later. First is the linear interpolation. It is the simplest method of getting values at positions in between the data points. The points are simply joined by straight line segments. Using the linear slope formula rise over run, we have the second value minus the value preceding it. As shown, we have y sub 2 over y sub 1 over x sub 2 minus x sub 1 derived up until we have the linear interpolation formula y is equal to y sub 1 plus x minus x sub 1 all over x sub 2 minus x sub 1 multiplied to y sub 2 minus y sub 1. And if we are to graph a linear interpolation equation or problem, the graph would look like this one. To understand it even more, let's have an example. Let's find a polynomial that interpolates the points 5, 6, and 7, 9. In linear interpolation, we need at least two set of points. Now, our x sub 1 is equal to 5, our y sub 1 is equal to 6, x sub 2 is equal to 7, and our y sub 2 is equal to 9. Given the linear interpolation formula, we're going to substitute our given values such that x plus x minus 5 all over 7 minus 5 multiplied to 9 minus 6. Simplifying the equation, we have 12 plus 3x minus 15 over 2. Simplifying the equation even more, we can conclude that the polynomial that interpolates the given example is 3x minus 3 all over 2. And if we are to graph that equation, it would look like this one. Next, we have the quadratic interpolation. This requires at least 3 points that will be useful to solve the problem, such that using the second-order polynomial to make the interpolation of the function. If we are to graph a quadratic interpolation equation, it would look like this one. I know this looks complicated, but I promise we will understand it even more through patterns and by applying it through different examples. An example just like this one. Let's construct a quadratic polynomial interpolation p sub 2 of x that interpolates the 3 points, -4, 5, 2, 2, and 5, 6. Inputting the given values all in one table, we have as shown in the presentation. Now for this problem, since we are up until the second polynomial interpolation, we have the formula p sub 2 is equal to b sub 0, which is the first y value, plus b sub 1, which is the first order of interpolation, multiplied to x minus x sub 0, the first value of x, plus b sub 2, which is the second order of interpolation, multiplied to x minus x sub 0, multiplied again to x minus x sub 1. Continuing on, so our b sub 0 is equal to 5 as shown. Our b sub 1, which is the first order of interpolation with the points -4 and 2, with the equation 2 minus 5 all over 2 minus -4, we have -1/2. And substituting all the needed values for our b sub 2, we have come up with the answer 11/54. Now take note of the 3 values we have now calculated. We'll be using that to substitute it on our quadratic interpolation formula, such that 5 plus -1/2 multiplied to x minus -4 plus 11/54 multiplied to x minus -4 multiplied again to x minus 1. Simplifying the equation, we have the final answer 17x² plus 118x plus 11 all over 54x. When graphed, this is what it looks like. Both linear and quadratic will be used in the next 2 methods we'll be discussing about. First, we have Newton's divided difference. The differences are found out successively between the 2 adjacent values of the y variable till the ultimate difference vanishes or become a constant. We can visualize the interpolation table with the table as shown. We have the first 2 columns where our given x and y values go. The next column is the first order of interpolation, next is the second order, and the third order. Now, the way I understood this lesson is by analyzing the pattern of how it is being solved, just like so. Our 0th order divided difference is always the first y value in the given table. Now we have our first order divided difference, our second order divided difference, and so on. General nth order interpolation. Given any n plus 1 point such x sub 0, f of x sub 0, x sub 1, f of x sub 1, x sub 2, f of x sub 2, and so on, we have this formula. See it? Seems familiar, right? Told ya! Linear and quadratic interpolation methods are the foundation and will be useful in solving for the polynomial interpolation and the value of f of x when x is in between of 2 given x values. Worry not just yet. To further understand what we are talking about, we'll be applying it to an example. Peter, a male seahorse, was rescued and was examined to be pregnant according to a team of marine biologists. The practitioners recorded the number of eggs released from Peter's body in each minute since it started. So f of x represents the number of eggs released, and x represents the minutes it has passed since he started releasing eggs. Here's their noted data after careful surveillance. Using Newton's divided difference, let's find the interpolating polynomials from orders 1 to 5 for us to solve for f of 3.14. we can calculate easily the problem using Microsoft Excel. So let's proceed to the other window.
So what we have here in our screen is my prepared template for the Newton's divided difference. So let's find the interpolating polynomials from first to fifth order to solve for f of 3.14. Now what we can see here is our given data table. Then we have retype those in their respective columns in our interpolation table that we have prepared beforehand. Now for this column, we're going to use the values here. So let's say in this cell, we are going to use these four values. Let me demonstrate. We have the f of x sub 1 minus f of x sub 0, as we can see here in our guide, close parenthesis, all over our x sub 1 minus the x sub 0. There we go. And we press enter. There we go. Now we see this is our b sub 1. Now let me hover my cursor over here. Then we're going to drag it up to this cell right there. Alright. Now if we could check each cell, we can see that they are using the four cells on the left side. Just so. We are not placing any value or equation right here since we are lacking any more values below these two columns. Now let's proceed to our second order of interpolation. We're going to have this 1 minus this cell all over. Since we're on our second order of interpolation, we're going to use, as we can see here, x sub 2 minus the x sub 0, close parenthesis, and we press enter. Now be careful, we don't do the hover and drag down a hack here. So we're going to input the equation one by one. Right, let's go. Let me just go ahead and do this. The value below it minus the one beside it all over x sub 2 minus x sub 0. There we go. Now we are again not inputting any equation in this cell since we'll be lacking another value needed from here. Okay, now we can check it one by one. We got it right. And let's proceed to the third order of interpolation. Just like so, we're going to use this one minus this cell on the left side all over. Since we're in the third order of interpolation, we're going to use the x sub 3 minus x sub 0. There we go. Now we're finally done from our first order of interpolation to the third. Let's proceed to our fourth. And again, we're going to use the cell right below it on the left side, like so, minus the one on its left side. Since we're on the fourth order, we're going to use the x sub 4 value, which is 4 minus x sub 0 value, and we press enter. Same thing goes. We're going to use this one minus this one all over x sub 4 minus, x sub 4 minus this x sub 0 value, and we press enter. Now for the last one, this is our fifth order of interpolation. This cell minus the value in this cell all over x sub 5, since we are on our fifth order of interpolation, minus x sub 0, and you press enter. Now we're finally done with our interpolation table. Now let's go ahead and proceed to use this formula we have shown earlier by substituting the value of b sub 0, b sub 1, b sub 2, b sub 3, and b sub 4, and b sub 5. Just like that, we're just going to substitute it as of the moment. Then for our final answer, we're going to use this equation, substitute the 3.14 to all x values in this equation. So as we can see on our formula bar on top of the screen, I have finally finished inputting the Excel formula derived from this equation, making sure all the operations are correct, making sure I have put enough parentheses, and making sure that I have used the b values we have here. Okay, and we're going to press enter, and we have this answer. But apparently we can't have the number of eggs in decimal, so let's round that up, and let's say we are estimating the number of eggs released from Peter's body to 113 at the 3.14 minute mark of the record. Therefore, we can conclude that the f of 3.14, or in the 3.14 minute mark, Peter has released 113 eggs. So we were tasked to find the interpolating polynomial. We have this equation, and we have also solved for the first to fifth order, and we have also calculated the f of 3.14 value, which is 113.
Going back to our presentation, I hope we're still catching up here. Next, we have the Lagrange method. This interpolation method is used to find the value of the function even if the data are not equally spaced. Also, it is used to find the value of independent variable x corresponding to a given value of a function. The Lagrange interpolation formula is a way to find a polynomial which takes on certain values at arbitrary points. It is named after an Italian-French mathematician named Joseph Louis Lagrange. Now, our L sub I of x are called our cardinals, and this also refers to the nth order polynomial. So when I say the second order polynomial in Lagrange's method, we are referring to L sub 2 of x. We have the Lagrange's method formula: p sub n of x is equal to f of x sub 0 multiplied to 0th order cardinal or polynomial plus f of x sub 1 multiplied to the first order polynomial in Lagrange's method, and so on and so forth. I hope you see the pattern and you will understand it even more in our examples later on. So let's consider the data given below coming from the population of the West City that was recorded every 10 years starting in 1990. Use Lagrange's method of interpolation to estimate the population in the year 2015. So this is our data table. Since we are calculating up until the p sub 3 of x, we'll be using the formula as shown. Let's solve for our L values. So our L sub 0 of x is equal to x minus x sub 1 multiplied to x minus x sub 2 times x minus x sub 3 all over x sub 0 minus x sub 1 times x sub 0 minus x sub 2 times x sub 0 minus x sub 3. Substituting the values, we have x minus 2000, since it is our x sub 1 in the given data table as shown on the left side, multiplied to x minus 2010, multiplied to x minus 2020, all over 1990 minus 2000, multiplied to 1990 minus 2010, multiplied again to 1990 minus 2020. Have you seen the pattern? I hope so. Now we have our first value in our L sub 0 of x, which is x minus 2000 multiplied to x minus 2010 multiplied to x minus 2020 all over negative 6000. Same pattern goes to the rest of the L values. So for L sub 1 of x, we have x minus 1990 multiplied to x minus 2010 multiplied again to x minus 2020 all over 2000. We have our L sub 2 of x is equal to x minus 1990 multiplied to x minus 2000 multiplied to x minus 2020 all over minus 2000. Here goes our L sub 3 of x. Substituting the values given from the problem, and we have our L sub 3 of x is equal to x minus 1990 multiplied to x minus 2000 multiplied to x minus 2010 all over 6000. Taking note of our L values, we're going to substitute it to our Lagrange's method interpolation formula. Taking note of the L values we have just calculated and our x value, which is now 2015, we are now substituting it to our Lagrange's method of interpolation formula, such that, as shown.
What kind of tea do you want? There's more than one kind? Did you make some of those up? I think I love sleepy time.
To simplify it, we have P sub 3 of 2015 is equal to 6,250 minus 39,687.5 plus 133,125 plus 47,812.5. And we have our final answer. By using Lagrange's method, the population in the year 2015 is estimated to be 147,500. Now, for the last objective of our discussion. Try it yourself through an assessment. Applying our understanding from the discussion, use both Newton's divided difference and Lagrange's method in solving for the interpolating polynomials from first order to fourth order and solve for f of 9. Given the data of the average number of users in each computer station and the average money in pesos earned from each station during Saturdays. Here's a tip. The answers of f of 9 from both methods should be the same. Feel free to pause the video and try it on your own. Let's review the answers. Here's the answer using the Newton's divided difference. We have f of 9 with the value 136.5. And using the Lagrange's method, we have the final answer, 136.5. So f of 9 using Newton's divided difference is 136.5 is the same as f of 9 using Lagrange's method, which is also 136.5. Got it? Congratulations! If you didn't, glad you tried. Try again. You'll get it on the next try. Now we're finally done with our discussion. I hope you have learned a lot and feel free to replay our video if there are some points that you need to review. Once again, this is CHARMIE 𝐂𝐔𝐑𝐕𝐄-𝅅. Thank you for watching. Don't forget to like and subscribe. Bye!